Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and problem sets. In today's solution to a homework problem that you've received, you have to rank the following molecules in order of increasing molecular dipole moment. You are asked to show all your work, and the molecules you're asked to look at are aluminum trichloride, AlCl3, NCl3, and NF3. Now, in many ways, this is a trick question. And also, it's an excellent question for a teacher to use because it tests you on a lot of aspects of material that we've covered in organic chemistry so far. In order to determine the dipole moment, you have to know the shape of the molecule. To know the shape of the molecule, you must know the hybridization of the central atom. This requires the hybrid orbital number, which requires lone pairs and atoms. And since I haven't given you the lone pairs, you must do the Lewis structure. So, what we're going to do is go stepwise for each molecule and try to get an idea of its dipole moment. In the case of aluminum trichloride, AlCl3, we'll do this one first, AlCl3, and we're going to do the total number of valence electrons. And the total number of valence of electrons for AlCl3, we can get this from the periodic table. Aluminum has 3 valence electrons, and chlorine has 7, so there's 3 times 7. And we have 21 for the chlorines, 24. So total number of valence electrons is 24. So we can take our aluminum, we can give it its 3 electrons, we can place our chlorine around it, and it has 1, 2, 3, 4, 5, 6, 7. The other chlorine, 1, 3, 5, 7. And the other chlorine, 1, 3, 5, and 7. And so we can line these up. And if I've studied my Lewis structure rules, I know that both boron and aluminum are an exception to the octet rule. They can form stable molecules. They may be reactive with an empty orbital. They may be Lewis acids, but they are stable with only 6 electrons. And so I will now draw actually, let's make a little more room here. Let's lower this a little bit. So I've got my aluminum. Give chlorine its lone pairs. Chlorine, lone pair, and chlorine, its lone pairs. So what we have here is aluminum trichloride showing all the lone pairs, and we can count the electrons to confirm we've done the proper structure. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 2, 4. So AlCl3, 24 electrons checks out. Now, we know lone pairs have dipoles pointing away from the lone pair, but I am only concerned, for simplicity's sake, we're going to assume we're only concerned with the dipoles and the lone pairs around the central atom. So I need to know the shape of the central atom. In order to do that, I need the hybridization, so I need the hybrid orbital number. The hybrid orbital number for aluminum is the total number of atoms plus lone pairs. And aluminum has 3 atoms, 0 lone pairs, so hybrid orbital number is 3. And that gives me a hybridization of sp squared. Now, what is the shape of sp squared? Well, the shape of sp squared is trigonal planar. Trigonal planar. Now, I have drawn the aluminum in a trigonal planar shape. It's sp squared. There are no lone pairs. I am ready to draw the dipole. And so what I'm going to do now up here is just draw the aluminum with the 3 chlorines and not draw the Lewis structure. Just put the 3 chlorines around it without the lone pairs on the chlorines and show the dipoles. Now, the dipole points to the more electronegative atom. Who's more electronegative, aluminum or chlorine? Well, we know chlorine's more electronegative, so the dipole points towards the chlorine. Each aluminum chloride bond is a single bond, they're all identical, and so you have 3 vectors, all equal strength, pointing to the corners of an equilateral triangle. If they were all pointing with equal strength and you add these vectors, the net result is they cancel each other. And so the dipole moment for aluminum trichloride is 0. Now let's continue this with NCl3 and NF3. Okay, so I'm going to redraw. We've got AlCl3. We've already done that. AlCl3 has a mu equal to 0. We are now going to do NCl3 and then NF3. Okay, so NCl3. NCl3, all right, I can do NCl3. Total number of valence electrons, and that equals nitrogen has 5, 3 times chlorine 7, it's 21, 26 electrons. So give nitrogen its 5 electrons, 1, 2, 3, 4, 5. Give chlorine its 7. All right. Give the other chlorine its 7. And give chlorine, another chlorine its 7. And I need 8 electrons around each atom. Chlorine has 8, chlorine has 8, chlorine has 8, and nitrogen now has 2, 4, 6, 8. So the Lewis structure I actually get out looks like this. Where I'm using dashes for lone pairs. Now we see nitrogen has a lone pair on it, so we're ready to calculate the hybrid orbital number. I can do this, the HON for the nitrogen. Equals 3 atoms plus 1 lone pair, or 4. So nitrogen is sp cubed. What is the shape for sp cubed? It's tetrahedral. So nitrogen is tetrahedral in shape if you count the lone pair. So we have to put in, and I'm going to draw the nitrogen and the chlorines again without the lone pairs around the chlorine. Now the chlorine lone pairs do produce dipoles pointing away from them, but they do cancel and they are weak, and they do have a small effect, but we can get a good picture without using them. So we're going, for simplicity's sake, not to use them. So here's my lone pair of nitrogen in its orbital. Now, who's more electronegative, nitrogen or chlorine? Very tricky. If I remember my trend for memory work for electronegativity, fluorine's greater than oxygen. Who's greater than nitrogen and chlorine? Nitrogen and chlorine are similar in electronegativity. For the purposes of our course, we assume them equal, so there's no dipole moment in the NCl bond. This means there is only a dipole moment due to the lone pair. And this means the NCl3 gets a mu due to the lone pair. A small mu to the lone pair. Now the question then becomes, is NF3 going to have a different dipole? Because NCl3 is greater, obviously, than AlCl3, who has a dipole of 0. Well, here's a question. Now, I could very easily change this question to NF3 because fluorine has the same number of valence electrons as chlorine, 7. So the total number of valence electrons for NF3 is the same. And if I go through this whole process, I can replace the chlorines here in my drawings with fluorines. Okay, so I could put F's here. And I would get the exact same thing. So essentially what you did for chlorine, NCl3, and the Lewis structure is exactly the same for fluorine. Now this one's probably the trickiest of the two because these chlorines become fluorine. So, just like NCl3, the lone pair, and we could go through the same calc, hybrid orbital number for nitrogen, 3 atoms plus 1, 4 sp cubed tetrahedral. Okay, so far everything looks exactly the same for NF3. But here's where the difference occurs, and it's a bit tricky. The lone pair has a dipole pointing up and away towards the electrons. Fluorine is more electronegative than nitrogen, so I'm going to use a different color for the fluorine dipole. I'm going to use black. Fluorine's more electronegative, so the dipoles point towards the fluorine. Now, if you've got 3 dipoles pointing out and away in a tripod triangular base in a tetrahedral shape, when you add these 3 vectors together, you end up with a small dipole down. The lone pair electron dipole is pointing up. So when you add the black dipole and the blue dipole together, you're going to get a mu, a Greek letter mu, equal to either a tiny blue up, because some is subtracted away from it, or a tiny dipole down. It depends who's greater, right? But the point is, if the black is a little greater than the blue, you'll get a dipole pointing down. Okay, so let's write or. Or if the black is smaller, you can have a tiny dipole up. It is unlikely that either dipole is so much greater than the other that they cancel so much that it would be bigger than the lone pair dipole. And so that means for here, NF3, you get, and I should exaggerate this maybe, you get a lone pair dipole. If that's the lone pair dipole, for mu for NF3, you get either a smaller dipole up or a smaller dipole down. There is the rare possibility that the black equals the blue and mu would be 0 also. But we'll assume that's not the case, that there is a small dipole in NF3 because the addition of the vectors for the fluorines does not equally cancel the blue dipole due to the lone pair. So the point here is that since the fluorine dipoles is opposed to lone pair, you either get a small dipole up or a small dipole down, but either dipole is smaller than the NCl3 dipole. So that's a bit tricky. So because of that, we can now give our ranking. And it was asked increasing order, meaning you start with the smallest one first. So AlCl3 is less than NF3, who's less than NCl3. So you've shown all your work, you've drawn all your solutions, and in fact on a test, you can't do what I did on my Scribblecast. You'd have to, even though it's identical in its solution, you'd have to show all your work for the NCl3 and the NF3. You'd have to draw both, but because they're so similar, you're literally just copying one from the other. Nevertheless, you'd show the work for all these structures. So everything I've drawn in the Scribblecast, you'd have to show on a test. Okay? So there you have it. AlCl3, a weaker dipole, zero dipole, less than NF3, and dipole moment less than NCl3. All right. Thank you very much.